Picture the postcard. Red rock towers cut into a rust-colored desert. A white salt flat so flat and so blinding that race car drivers have used it for 100 years to break the world land speed record. A lake so salty that swimmers float on top of it without trying, and so still it looks less like water than like a sheet of hammered metal under the sun. That's the Utah everyone already carries in their head before they ever set foot in the state. Stand on that salt flat in person and the postcard gets more intense, not less. Heat rises off the white crust in visible waves even in cool months. The ground crunches underfoot like packed snow, and in places it's hard enough to land a small aircraft on. Sound behaves strangely out there too, carrying flat and far across a surface with nothing to interrupt it for miles in any direction. It feels like the edge of the world, or the bottom of one that used to be somewhere else. Now take one detail out of that postcard and replace it with a fact that most people standing on that exact ground don't know. The runways of Salt Lake City International Airport sit on what used to be the floor of a massive lake, one that at its deepest point buried the valley under more than 1,000 feet of water, an inland sea so large it would have swallowed Lake Michigan whole and still had room left over. And that lake vanished fast. Part of it disappeared inside of about 2 months, during a flood so large that when geologists first found evidence of it, more than 100 years passed before anyone believed what they were looking at. That flood and the vanished sea that caused it is the real shape hiding underneath almost everything people think they already know about Utah. The Salt Flats, the Great Salt Lake. Even the mountains ringing Salt Lake City carry a scar from it, a straight, level line cut into solid rock like a bathtub ring, visible from a commercial airplane window if you know where to look. This is the biography of that lake, where it was born, what built it, what broke it, and what it left behind. Because what it left behind is still changing today, faster than at almost any point in the last 12,000 years. Start with the scar on the mountains, because once it's pointed out, it can't be unseen. Drive along the base of the Wasatch Range, on the east side of Salt Lake City, and look up at the foothills. Above the neighborhoods, and the university, and the state capitol, the slope changes. There's a bench, a flattened shelf cut horizontally into the mountainside, running for miles at almost exactly the same elevation. Keep driving and it stays level, mile after mile, indifferent to whatever ridge or canyon happens to be underneath it. Nature doesn't usually build in straight lines. Rivers meander. Slopes erode unevenly. A perfectly level shelf carved into rock for dozens of miles in a row is a shoreline. Not the shoreline of the Great Salt Lake sitting in the valley today, but the shoreline of its enormous ancestor, cut by waves lapping against that exact elevation for centuries at a stretch, back when the valley floor below it was buried under water so deep that this shelf was nowhere near the surface. Geologists call that lake Lake Bonneville, named for an Army officer, and it's the reason this part of Utah looks the way it does now. To understand the mystery and the flood and the strange, unstable present the Great Salt Lake is living through, you have to go back to how a bone-dry desert became the floor of a body of water bigger than any lake in the modern United States outside the Great Lakes. Utah sits inside something called the Great Basin, a stretch of the American West between the Wasatch Range and the Sierra Nevada, where every river that starts flowing has nowhere to go. Rivers elsewhere eventually reach an ocean. Rivers in the Great Basin dead end, either soaking into desert ground or pooling into lakes that have no outlet at all. A basin like that behaves like a bathtub without a drain. Whatever water flows in has exactly one way to leave, and that's evaporation. For most of the last several million years, that arrangement kept the Great Basin dry, because in a hot climate, evaporation keeps pace with rainfall, and the water never has a chance to pile up. But roughly 30,000 years ago, During the last ice age, the climate over the American West flipped. Temperatures dropped. Storm tracks that normally passed farther north drifted south instead, dumping rain and snow across the Great Basin at a rate the desert hadn't seen in ages. Evaporation slowed in the cooler air, while the inflow from rivers, streams, and melting mountain snowpack kept climbing. The bathtub started filling faster than it could drain. It kept filling for thousands of years. Not in a dramatic surge, but the way a bathtub actually fills, gradually, a little more water every season than left through evaporation the season before. Streams that are barely creeks today were feeding a rising sea. And because the basin had no outlet, there was nothing to stop the level from climbing except the height of the rim around it. By around 18,000 years ago, Lake Bonneville had grown into one of the largest lakes on the continent. At its peak, it covered nearly 20,000 square miles, a footprint that swallowed most of western Utah and reached into what's now Nevada and Idaho. In its deepest basin, the water sat more than 1,000 feet above the lake bed, deep enough to bury a modern skyscraper more than 3 times over with room to spare. By total volume, scientists estimate the lake held somewhere around 10,400 cubic kilometers of water, enough that if you tried to picture it as a single cube, each side of that cube would stretch about 22 kilometers, taller than any mountain on the continent. This is where the shelf on the Wasatch foothills comes back into the story. A lake that size, sitting at roughly the same elevation for centuries, does exactly what an ocean does to a coastline. Waves chew away at the shore. Sediment builds terraces. Over enough time, the water carves a level bench into whatever rock or soil happens to be sitting at the waterline, and it keeps carving at that same elevation as long as the lake surface holds still there. Lake Bonneville held still at several different elevations for long enough stretches that it left not one shoreline, but several, stacked one above another like rings on a tree, each one marking how long the lake paused at that particular height before rising again. A geologist named Grove Carl Gilbert spent years in the 1870s and 1880s riding across the Utah desert on horseback, mapping those terraces one by one. He was the first person to piece together that the benches cut into mountainsides all across the region, from the Wasatch Front to ranges more than 100 miles apart, lined up at matching elevations. That meant they couldn't be local erosion. They had to be shorelines of one single enormous lake that had once connected all of those mountains at once. Gilbert named the lake after Benjamin Bonneville, an Army captain and explorer, and the name stuck even though Bonneville himself never saw the ancient lake and had nothing to do with discovering it. Gilbert's work became one of the founding studies in American geology, and the terraces he mapped are still called the Bonneville Shoreline, the Provo Shoreline, and the Stansbury Shoreline today, named for the elevations where the lake paused longest. Gilbert did this work without any of the dating tools scientists rely on today. He could map where the shoreline sat, but he had no reliable way to know exactly when the lake reached each one. Modern researchers filled that gap later using radiocarbon dating on shells and organic material buried in the old lake sediments, along with cosmogenic dating on exposed boulders, a technique that measures how long a rock surface has been sitting in open air. Layered together, those methods let scientists reconstruct not just where Lake Bonneville's edges sat, but a rough timeline of when the lake rose, when it paused, and when it finally broke through Red Rock Pass, turning Gilbert's 19th century fieldwork into a dated physical history instead of just a map of terraces. A closed basin with no outlet can only rise so far before physics forces a decision. Lake Bonneville kept climbing through the Ice Age, fed by that same wetter, cooler climate, and every few thousand years it reached a new record height. But a basin has a limit. Somewhere along its rim, there's always a lowest point. And once the water reaches that point, gravity takes over and the lake becomes a river spilling over a dam. For Lake Bonneville, that low point sat far to the north, near the modern border between Utah and Idaho, at a gap in the hills called Red Rock Pass. And the pass wasn't made of solid granite. It was built from loose material, alluvial fan gravel washed down from surrounding slopes over thousands of years, mixed with softer limestone riddled with underground channels. In engineering terms, it was the geological equivalent of a dam built out of loose gravel instead of poured concrete. It could hold back a lake for a long time. It couldn't hold back that lake forever. As the water crept toward the top of Red Rock Pass, it began to do what water does to loose gravel. It seeped through, then trickled, then ran in shallow channels across the surface of the pass itself. Each bit of flowing water carried away a little more material, cutting the channel slightly lower, which let slightly more water through, which cut the channel lower still. It's the same feedback loop that turns a small crack in a dam into a catastrophic failure. Except this dam wasn't built by engineers who could reinforce it. It was built by nothing more than gravity, sediment, and time. And once the erosion crossed a certain threshold, there was no mechanism left to stop it. About 18,000 years ago, that threshold broke. The channel across Red Rock Pass tore open, and Lake Bonneville, one of the largest lakes in North American history, began draining north into the Snake River Basin in Idaho at a rate almost impossible to picture. At its peak, the discharge through the gap reached roughly 1 million cubic meters of water every second, close to 35 million cubic feet per second. To put that in perspective, that's somewhere around 500 times the largest flow ever measured on the Snake River in the modern era, moving through a single gap in the hills that, weeks earlier, had just been a quiet, grassy pass. The flood tore across what's now southern Idaho with enough force to strip topsoil down to bedrock, gouge canyons, and carry boulders the size of small cars for dozens of miles. Geologists now estimate the peak flow lasted for roughly 8 weeks before easing, though the broader flood event and its aftermath played out over a longer stretch. By the time the outburst finished, Lake Bonneville had lost close to 4,750 cubic kilometers of water, and its surface had dropped by more than 350 feet almost overnight in geological terms, settling at a new, permanently lower shoreline that Gilbert would later name the Provo level. Picture the scale of that for a moment. In the days before the breach, Red Rock Pass was a quiet saddle in the hills, grass moving in the wind, maybe a few animals grazing near a trickle of overflow. Within a span of hours to days, that same gap was carrying a volume of water estimated at nearly 5 times the average flow of the Amazon River, the largest river on Earth today, funneled through a channel only a few miles wide. Anything living directly in the flood's path was stripped away almost instantly. Downstream in Idaho, the water moved fast enough and carried enough force to pluck basalt boulders the size of small cars out of the ground and roll them for miles, the way an ordinary stream tumbles pebbles. Nothing on that scale has happened anywhere on the continent since humans have been keeping written records of it. Here's the part of the story that took geologists the longest to accept. For decades after Gilbert's original work in the 1870s, nobody connected his shoreline maps in Utah to something strange, sitting more than 100 miles north, scattered across the Snake River Plain in Idaho. Farmers and travelers kept finding enormous rounded boulders, some more than 10 feet across, sitting out in open country with no glacier, no mountain slope, and no ordinary river anywhere nearby capable of moving rocks that size. Locals joked that they looked like giant petrified watermelons, and in the 1950s, a roadside billboard actually advertised them that way as a tourist curiosity. It took until 1955 and further published research through the early 1960s for geologists Harold Mauld and Howard Powers to prove what had actually happened. Those boulders, which came to be formally known in the geological literature as melon gravel, weren't local at all. They were the wreckage of the Bonneville flood, hurled and rounded and carried for dozens of miles by a wall of water that no living person had ever seen, and that most geologists until then hadn't believed was possible. The evidence had been sitting out in open fields for decades. What finally changed was that geologists believed it. draining through Red Rock Pass didn't empty Lake Bonneville. It only knocked the water down to a new, lower shoreline, the Provo level, where the lake stabilized and sat for another few thousand years while the Ice Age wound down. But the Ice Age was ending everywhere, not just in the Great Basin. As the climate warmed through the end of the Pleistocene, the same conditions that had built the lake began running in reverse. Storm tracks shifted back north. The desert around the Great Basin dried out again. Evaporation started outpacing inflow, and without an ice age refilling the bathtub, the lake had nowhere to go but down. It shrank for thousands of years, not in one dramatic event this time, but through the same slow, patient process that built it, running in reverse, evaporation carrying away more water every year than the rivers replaced. As the lake retreated, it left the desert floor coated in dissolved minerals, salts that had been washing in from surrounding mountains for tens of thousands of years, and had nowhere left to go once the water carrying them disappeared into the air. Where the water pooled longest and evaporated most completely, thick beds of salt built up on the valley floor. That mineral crust is what people now call the Bonneville Salt Flats, a flat, blinding white expanse west of the modern lake that owes its existence directly to the ancient lake's slow death. What survived in the deepest remaining low points of the old lake bed were the last puddles of a sea that had once covered almost a fifth of the state. The largest of those remnants is the modern Great Salt Lake. Others include Utah Lake to the south, which stayed freshwater because a river still flows through it, and Sevier Lake, which today sits dry for most of the year, an empty white playa that only fills briefly after unusually wet winters. None of these modern lakes are separate stories. They're all fragments of the same original body of water, cut apart by thousands of years of evaporation, the way a puddle left on pavement breaks into smaller and smaller pools before it finally disappears. People arrived on the shrinking shorelines of this lake system long before anyone wrote its history down. Fremont farmers and hunters settled along its wetlands and rivers for centuries, and the ancestors of the northwestern band of the Shoshone Nation, the Gauchute, and the Ute peoples built parts of their lives around the marshes, waterfowl, and fresh water where rivers like the Bear and the Jordan met the retreating lake. Those wetlands were never just scenery to the people living there. They were the pantry. Long before anyone talked about a migratory bird crisis, those same marshes were already one of the richest food sources in the entire Great Basin, and the tribes who depended on them understood the lake's rises and retreats in a way that predates every geologist who later gave the lake its scientific biography. That process never actually stopped. It only slowed down enough that for most of human history in the region, the Great Salt Lake looked stable from one generation to the next. That stability is now visibly breaking. In November of 2022, the Great Salt Lake dropped to the lowest elevation ever recorded, a little over 4,188 feet above sea level. At its healthiest modern extent, the lake used to cover close to 1,700 square miles. At that record low, it had shrunk to somewhere around 800, losing roughly two-thirds of its surface area within living memory, not over geological time. That record low set off real alarm. In January of 2023, close to 36 scientists and water researchers published an open letter warning Utah lawmakers that without a dramatic and immediate increase in water reaching the lake, the Great Salt Lake could functionally disappear within about 5 years. By their estimate, the lake had already lost close to 3/4 of its historical water volume and exposed roughly 60% of its lake bed. Then, that same winter, an unusually heavy mountain snowpack, more than double the historical average by spring, sent enough runoff into the lake to raise its level by about 3 feet in a matter of months. A second strong snow year followed in 2024, and Utah lawmakers passed new water conservation measures and formed a strike team to coordinate the state's response. The lake climbed off its absolute floor, but researchers who study it are clear That a couple of good winters isn't the same as a fix? Recent measurements still put the lake several feet below the elevation scientists consider healthy for the long term, which means the underlying imbalance between water use and water supply that produced the 2022 record low hasn't gone away. It has only been interrupted. Scientists studying the Great Salt Lake have pointed to a grim parallel on the other side of the world. Central Asia's Aral Sea was once one of the four largest lakes on the planet before Soviet-era irrigation projects diverted the rivers that fed it, and within a few decades it shrank by more than 90%, leaving behind a toxic, wind-scoured desert and collapsed fishing towns along what used to be its shore. Researchers who study the Great Salt Lake have cited that collapse directly as the outcome they're trying to prevent, not as a distant cautionary tale, but as proof of how quickly a large saline lake can unravel once withdrawals outpace inflow for long enough. The causes aren't mysterious the way Red Rock Pass once was. Rivers that used to feed the lake are diverted upstream for farms, lawns, and a metropolitan area that has grown enormously around Salt Lake City in the last 50 years. Add a warming climate on top of that diversion, and the lake is losing water faster than the mountains can resupply it. The same imbalance that shrank Lake Bonneville after the Ice Age, just running on a time scale of decades instead of millennia, and driven this time mostly by people rather than climate alone. The consequences reach past the lake itself. As water retreats, it exposes lakebed that has been catching windblown and waterborne pollution for well over a century, and that exposed sediment doesn't stay put. When storms pick up dust from the dry lake bed, they carry it toward the 2 million people living in the Salt Lake Valley, and that dust carries traces of arsenic and other heavy metals embedded in the old lake sediment. The lake's chemistry also supports an entire food web most visitors never think about: brine shrimp and brine flies, that in turn feed something like 10 million migratory birds that stop at the Great Salt Lake every year on their way across the hemisphere. Shrink the lake enough, and that food web starts to fail along with it. The Bonneville salt flats are shrinking too, and for a more direct reason. Since 1917, companies have pumped mineral-rich brine from underneath the salt flats to extract potash, a mineral used mainly in fertilizer. Pulling that brine out reduces the amount of salt available to precipitate back onto the surface crust each year. Between 1960 and 1988 alone, the salt flats lost more than 55 million tons of salt, and the crust that racers depend on for high-speed runs thinned from about 7 feet down to roughly 5.5. Today, the flats cover only about half the surface area they held at their peak in the 1990s. Efforts to pump leftover brine back onto the flats to slow the loss began in the late 1990s, and after decades of study, they haven't been enough to reverse the trend. There's one more piece of this story that captures the whole biography in a single object. In 1970, an artist named Robert Smithson built a sculpture at the edge of the Great Salt Lake called Spiral Jetty, a coil of black basalt rock and earth, about 6,000 tons of material, stretching roughly 1,500 feet out into the water in a shape that curls counterclockwise, like a fossil. Smithson built it during a low water period, and just 2 years later, rising lake levels swallowed it completely. For roughly the next 3 decades, Spiral Jetty sat entirely underwater, visible only in photographs, until drought finally exposed it again in 2002. In the years since, as the lake has kept dropping toward and past its historic lows, the jetty has emerged further than at any point since it was built. Its black rock now crusted white with salt, sitting on cracked mud that used to be lakebed. A piece of art meant to comment on impermanence has ended up as an accidental measuring stick for exactly how much water the Great Salt Lake has lost, decade by decade, in real time. Stand at the edge of the modern Great Salt Lake today, and it's easy to see it as a fixed feature, a static blue smear on every map of Utah, unchanging the way mountains and deserts are assumed to be unchanging. That was never true. The lake in front of you has already been rewritten several times over. It's the current chapter in a story that began with an ice age flooding a closed desert basin, was violently rewritten by one of the largest floods in the continent's history, spent thousands of years quietly evaporating down to a handful of surviving puddles, and is now being reshaped again. This time mostly by human water use, layered on top of a warming climate. Go stand at Spiral Jetty. Robert Smithson built that coil of black basalt in 1970 as a sculpture about impermanence, and the lake swallowed it within 2 years, sat on top of it for 3 decades, then dropped low enough in 2002 to hand it back, and has kept dropping ever since. What you're looking at now is black rock crusted white with salt, sitting on cracked mud that used to sit 1,000 feet underwater. The whole billion-year, Ice Age, flood-scarred biography of this place, compressed into one coil you can walk out to and touch. None of that makes Utah less familiar. If anything, it makes the familiar version more accurate. The mystery here was never really about a hidden location or a secret nobody had seen. Farmers in Idaho were staring at the melon gravel boulders for decades before anyone connected them to a vanished flood. The shoreline on the Wasatch foothills has been visible to every driver on the interstate for as long as the interstate has existed. The mystery was that nobody had assembled the pieces into their actual shape yet, and once Gilbert, then Malday and Powers, then generations of hydrologists after them did assemble it, an ordinary desert turned out to be the drained floor and shrinking remnant of one of the largest lakes the continent has ever produced. And it's still changing under everyone's feet. If this is the first time you have looked at a Utah salt flat or the Great Salt Lake and actually understood what you were looking at, that's the whole point. Hit like if the mountainside shoreline detail got you, subscribe for more of these hidden in plain sight geology stories, and drop a comment with the elevation you would guess your own hometown sits above or below an ancient shoreline like this one. There's usually one closer than people expect.